All right, let's get into one of the most absolutely mind-bending ideas in all of physics. We are going to explore a theory that suggests our reality, well, it's just one of countless others, all existing right alongside us, in parallel. So, think about this for a second. The choice you just made to watch this explainer. According to this idea, that simple click might have literally split reality itself, right? In one universe, you're here with me, but in another, a version of you clicked away and is already watching something else. This is the wild core idea of what's called the many worlds interpretation. But hang on, why would anyone even come up with such a radical idea? Well, it all goes back to a huge conflict that just shook physics to its core. And this famous quote from Einstein, it perfectly captures his frustration with quantum mechanics. He just hated the idea that at the most fundamental level, the universe runs on pure random chance. You see, before this whole quantum revolution, the universe felt, well, it felt knowable. Physicists pretty much saw it as this grand, intricate clockwork machine, just ticking along, following these precise and totally unbreakable laws. For centuries, this was the view of reality, and the perfect analogy for it is a giant cosmic billiards table. The idea was if you could just know the exact starting position and the momentum of every single particle, you could, in theory, predict the entire future of the universe with perfect accuracy. This whole idea has a name: causal determinism. And it's a really comforting, orderly way to see the world, cemented by Isaac Newton's laws way back in the 17th century. Everything has a cause. That cause leads to a predictable effect. Simple, elegant, and for a really long time, it seemed totally unshakable. But then, in the early 20th century, this new science came along. And, well, it basically broke the machine. Quantum mechanics introduced this baffling new ingredient right into the heart of physics: pure, unadulterated randomness. And all of a sudden, physicists discovered that down at the subatomic level, things could happen for no apparent cause at all. Like, you can't predict exactly when one specific radioactive atom will decay. It just does. And this wasn't just about us not knowing enough. The randomness seemed to be a fundamental feature of reality itself. So there it is, the big showdown, laid out right in front of you. On one side, you've got the classical world of predictable billiard balls, and on the other, the quantum world of random atomic decay. I mean, this wasn't some small puzzle. It was a deep, deep contradiction at the very foundation of physics. And Einstein, he hated it. The burning question was, how could both of these possibly be true? And this brings us to our hero. Faced with this quantum mess, a brilliant and, frankly, audacious graduate student named Hugh Everett proposed a solution that didn't try to get rid of the weirdness. No, he embraced it in a way nobody had ever imagined. So, in 1957, Everett looks at this whole timeline, from Newton's predictable clockwork universe to the dice-rolling quantum world, and he offered a way out. He suggested that maybe, just maybe, determinism wasn't dead after all. Maybe we just weren't looking at the whole picture. He originally called it the relative state formulation, but today we know it as the many worlds interpretation, and its core claim is just radical. He argued that this thing called the wavefunction, which is the math that describes all the possibilities for a quantum system, is the only thing that's actually real. There's no sudden random collapse where reality is forced to pick just one outcome. So what does that really mean? It means the universe doesn't choose a path. When it's faced with a quantum choice, it takes all of them. Reality branches. So instead of one single timeline, what you have is this ever-expanding tree of parallel universes. And every single one is just as real as our own. The famous Schrödinger's cat experiment is the perfect way to wrap your head around this. So before you look in the box, the cat is in what's called a quantum superposition. It's both alive and dead at the same time. Now, the standard view says that opening the box forces reality to randomly pick one. But Everett's theory says, nope, the moment you observe that cat, the universe itself splits. In one branch, you find a live cat, but in another, a parallel you finds a dead one. Both things happen. Both are real. Now, as you can probably imagine, this idea of creating countless new universes every single second, it didn't exactly sit well with everyone. The theory, while it's mathematically elegant, comes with its own set of pretty profound problems. Okay, so these are the big three hurdles. First, Occam's razor. You know, the principle that the simplest explanation is usually the right one.
I mean, creating infinite universes seems like the opposite of simple, right? Second, you've got the probability problem. If everything that can happen does happen, why does quantum mechanics give us such precise probabilities? And third, the preferred basis problem, which is a fancy way of asking, why does reality split along these clean, classical lines, like a cat being either alive or dead, instead of some weird, mushy quantum mix of the two?
So the folks who support many worlds have a pretty clever answer to that Occam's razor argument. They say, look, you can have a simple universe or you can have simple laws, but you can't have both. Many worlds chooses simple laws. It gets rid of that messy, poorly understood collapse idea and just lets the basic math of quantum mechanics do its thing. And in that sense, it's actually more economical.
And what about seeing a stable reality instead of some quantum blur? Well, the modern answer is a process called decoherence. A good way to think about it is like a tuning fork. A quantum state is like that vibrating fork. It can produce lots of possible notes at once. But as soon as it interacts with the air around it, the environment, it's forced to settle on just one clear, stable note. That's decoherence. It explains why branches form along familiar lines like alive or dead, without needing some special collapse rule. So after decades of debate, where does the theory actually stand today? Well, at first it was seen as completely preposterous, but its fortunes have changed dramatically. For years, Everett's idea was basically dismissed as science fiction. I mean, it was just part of his PhD thesis, and even his own famous advisor was super skeptical. But the math behind it was solid, and as problems with other interpretations just kept piling up, physicists started to take another look. Today, it is a serious mainstream contender. In fact, there was a well-known poll of leading physicists, and while, it was conducted a while ago, it found that a surprising majority actually believed many worlds is true. Now, a poll isn't scientific proof, of course, but it just goes to show you how far the theory has come from being this fringe idea. It's really a testament to the power of its mathematical elegance. And this isn't just a philosophical debate. The many worlds framework is actually incredibly useful in certain fields. In quantum computing, the whole idea of a calculation happening in many parallel states at the same time, it's a perfect fit. And in quantum cosmology, it lets physicists describe the entire universe with quantum mechanics without needing some outside observer to make things happen.
And this all brings us to the final, unsettling question that lands right back on you. If this theory is correct, there are countless versions of you out there, living out the consequences of every single choice you did and didn't make. The version that took that job, the one that didn't, the one that said yes. So the question becomes, which one of them is the real you? Or are you all of them? That is a question physics can't answer, and it leaves us to wonder about the universe and the version of ourselves living just next door.